Hello mathematicians, let's have a quick review now of simple harmonic motion, where simple harmonic motion is an example of motion with non-uniform acceleration. And in particular, the acceleration in simple harmonic motion is periodic, in the sense that it's proportional to the displacement and it's always directed back towards the equilibrium position. So the equation which describes it is this. So we can see that K, in a sense, is a constant of proportionality. So A is proportional to X, is covered by Kx, and that it's directed back towards equilibrium is covered by this negative sign here. More specifically, we can write the acceleration as a function of time as minus omega squared x, where omega, which is sometimes referred to as n, is equal to the angular velocity of the simple harmonic motion. And that will make a little bit more sense if we recognise, as we'll see later on hopefully, that simple harmonic motion is a projection of uniform circular motion onto one dimension. In any case, n, the angular velocity, is equal to 2 pi on t, and t is the period of the simple harmonic motion, which is the time it takes to complete one oscillation. So depending on where the particle starts, so let's suppose it starts here in the middle and it's heading to the right, one complete oscillation would be out to the extreme, back through the equilibrium position, out to the other extreme, and back to the equilibrium position. There are things that characterise simple harmonic motion, which include the fact that at the equilibrium position, the velocity is a maximum. The particle is moving its fastest just there. And the acceleration is actually 0. So x dot equals 0 just there. When we get out to the extreme position, which is maximum amplitude, velocity is 0 and acceleration has its maximum magnitude, and likewise at the other extreme. So we can get some position-dependent equations for simple harmonic motion as follows. Now I'm going to use the extension 2 technique, where my starting point is that v dv dx is equal to acceleration, whether I do the x double dot or whatever. Now I'm then going to multiply this across, so v dv equals a dx, and then I'm going to integrate both sides. And I'm going to, when I put those integrals in there, it means that I'm integrating this expression with respect to v and this expression with respect to x. So to do this, I need a as a function of x. And that is my definition in simple harmonic motion, that a is actually negative k times x, or use k as negative omega squared. So I've got that my integral here becomes this, so I put my limits in, so the particle is going to go from some value of velocity to 0 at one extreme, and it's going to go from some value of x to x maximum at the extreme, and that thing that I'm going to integrate, a, is minus w squared x. So when I carry out this integration, I've got v squared on 2 from v to 0 minus omega squared x on 2 from x to x max, and when I do that I get this expression here. If I multiply right through by 2, I get the expression that you're familiar with from extension 1, that v squared equals omega squared, where omega is 2 pi on the period, outside of the amplitude squared minus the actual position of the particle squared. And just, again, check for yourself that that corresponds with what we know physically about simple harmonic motion, the points where we get maximum and minimum velocity. Now, simple harmonic motion may also be described in terms of time. So if we describe simple harmonic motion which begins from the equilibrium position, x equals a sine omega t, where a is the amplitude of the motion, not the acceleration, is a solution of our equation for simple harmonic motion. So the time-dependent equations for simple harmonic motion are this, x equals a sine omega t, which we can see drawn just here, which shows that the particle goes from 0 out to maximum amplitude, back through equilibrium, maximum amplitude, the other direction, and so on. If we differentiate that with respect to time, we get omega a cos omega t. And if we tried to sketch the curve there, we would see that when x equals 0, x dot would be a maximum value because it would now be a cos curve. When x equaled maximum, then x dot would be equal to 0, and so on. So we could sketch up the cos curve on here. But of course this axis would mean something different. And if we took our velocity equation and we differentiated that again, then what we would get would be minus omega squared a sine omega t, and this part, a sine omega t, is x, so we've got our, as expected, equation for acceleration as a function of displacement, and we can see that that will just be a curve which is the minus of this curve in terms of how it varies. So we have maximum acceleration at the extremes and zero acceleration when we have zero displacement. Now, if the motion starts from the extremes, then depending on which way the particle is travelling, plus or minus a cos omega t will be solutions also, and for any other positions in between, we can take a sine omega t plus a phase shift, phi, or we can actually write some combination of sine and cos as well. Now let's have a look at a question from the 2017 Extension 1 paper. So we're given one statement about the value of displacement and velocity, and another one. We can see that as the displacement gets bigger, the velocity is decreasing. So when we try to put all of this into perspective and draw our picture, something like this comes to mind. So we know that at equilibrium, when x equals 0, our velocity is a maximum. These 2 points were specified, and somewhere out here at maximum amplitude, the velocity will actually be 0. And we're asked to find the period of the motion. So if we start from our position-dependent equation for acceleration, we know that we could derive this by integration, and then we substitute in what we've got. So we have those two values, plug those in. Now that gives us two unknowns, so then we've got our second set of data, so two equations, two unknowns. We solve those simultaneously by dividing one equation by the other. So we get this, and plug it into this, solve that, get our value for n, and we need our value for n to be able to get the period because n is 2 pi on t. So we have that t is 2 pi root 3 seconds.